Welcome back to section 4 of chapter 2. In this section, we are going to be looking at some applications of the derivative, some of them involving rates of change or velocity, some of them involving some economic applications, including marginal cost and revenue, things like that. And we'll be looking at some free fall equations and stuff like that as well. So our learning targets for the day: I can find rates of change of areas and volumes. I can estimate velocities from graphs. I can answer questions about an object's movement from a graph of its velocity. I can solve applications involving velocity and other rates of change. I can answer questions about an object's movement from its position function. So, an instantaneous rate of change is at a point, the instantaneous rate of change of a function at a certain point is the derivative of that function at that point. So we would find the derivative and then just plug in that point. So if we have something like circles, if we're going to be finding an instantaneous rate of change at something, we'd start out with a formula, an equation. So we know that a circle, it'll probably ask like how fast is the area of a circle changing when the radius is a certain amount as the circle is increasing. And so the area equals pi r squared. And so we can find the derivative with respect to r. R is going to be our variable here. And so dA over dr, the derivative, we just multiply by 2, so we'd have 2 pi times r. So what does 2 pi r look like? That's the area, or that's the equation for the circumference. Weird. Also weird, if we go 3 dimensions, the volume of a sphere, the derivative gives us the surface area formula. It's beautiful. And so anyway, so we have the rate of change of the area with respect to r now. So if we want to know how fast is the area changing when r equals 3, we would just plug in 3. dA over dr equals 2 times pi times 3, which would be 6 pi. And now it's going to have units, right? Because we're measuring these things in units. So the area is going to be square units. The r is going to be just a normal units. So let's say we were in centimeters. So this would be 6 pi square centimeters per centimeter. Now this would not be reduced. Like you wouldn't reduce it because this is a rate. This is square centimeters of area for every 1 centimeter of radius. And so that's the units. For the units for rate of change, you literally take the rate of change of the first, or the units of the first thing, divide by the units of the second thing. That gets our that gets our units for our rates of change. So circles is something that you'll see a bit of because it has a nice little area there, or a nice equation. We could do cubes too. We could look at the volume of a cube. We could do the surface area of a cube, but surface area of a cube is going to be 6 times x squared, where x is side length. So we could do the surface area, but I think doing volume could be more fun. So the rate of change of the volume, dv over dx, we multiply by 3, so we have 3x squared. So what is the rate of change when the side is 2 feet? We have a big cube, it's increasing, and we want to know how is the volume changing when the side length is 2 feet. So our dv over dx is going to be 3 times 2 squared. 2 squared is 4 times 3 is going to be 12 cubic feet of volume for every foot added to the side. So that's how to deal with some of these, especially initial questions. We have a shape, and so it's changing. Each one variable is acting on the other variable. We will see this a bit more in the next chapter when we add multiple variables. Like here we have a cube. What if we had a rectangle that wasn't just a cube? How would we deal with that? We'd see that later. Right now we just have one variable in there. So that kind of limits what we can work with. Instantaneous velocity. So we've talked about rates of change. Velocity. The instantaneous velocity is the derivative of the position function. So if we have our position function, which a lot of times is s, it could be s of t or f of t sometimes also, then the velocity is just the derivative of that. The instantaneous acceleration is a derivative of the velocity function. So a of t equals v prime of t. So we'll be doing a bit with velocity and acceleration here in just a second. First, we're going to look at a velocity graph and see what we can tell about the function and about the acceleration. So again, notice this is velocity, shows a velocity graph. So when is the particle moving forward? When is it moving backward, speeding up, slowing down? So we'll actually talk about speeding up and slowing down a little bit, but we can do it now. So when is it moving forward? It's moving forward when the velocity is positive. When is the velocity positive? It's positive when it's above the x-axis. So it's moving forward from 0 to 1. And from 5 to 7. When is it moving backwards? This is forward. Backwards when it's negative. So from 1 to 5. And that's it, because it never goes negative again. Speeding up and slowing down, it is speeding up and slowing down, or it's speeding up when the velocity and the acceleration have the same sign, is when it's speeding up. So if we're moving forward and we're increasing speed, so both the velocity and the acceleration are positive, we're speeding up. If we're moving backwards and the acceleration is negative, that means we're moving backwards even faster. That means we're speeding up. So when do the velocity and acceleration have the same sign? This is kind of a weird place for this question. Let's come back to that after B, because B, when is a particle's acceleration positive, negative, and 0? So I'm going to just leave a little bit of space here. So the acceleration is the derivative of the velocity. So it's the derivative, it's the slope of this graph. When is it negative? It's negative right here and right here. So it's negative on 0 to 2 and 6 to 7. It's positive when it's going up, which will be from 3 to 6. And then it's 0 when the slope is 0, which is going to happen here and also here. So from 2 to 3 and from 7 to 9. That's when the acceleration is not changing. So, and then, yep. So now going back to that question A, when is it speeding up? It's speeding up when either the velocity is negative and the acceleration is negative, or when they're both positive. So we can look at, I'm going to erase some of my marks over here. We can look at, when is the velocity negative? It's negative when it's down here. Well, when is the acceleration also? When is the slope there negative? Here. So it's speeding up from 1 to 2. And then how about when it's positive? Well, this is the only time when the acceleration is positive. And so here's when the velocity is positive. So from 1 to 2 and from 5 to 6. It's slowing down when they have different signs. So from 0 to 1 and from 3 to 5. When the acceleration is 0, it's just holding a constant velocity. It's neither speeding up nor slowing down. Oh, and then from 6 to 7 as well. Because we have this where its acceleration is negative, but it's positive. So looking at the graph, if we want to think about that, if we're just looking at this first little spot, so our velocity is positive, but it's getting closer to 0. That means that it's a decelerating, right? Because our velocity is slowing down. When we get down here, we're starting at 0, and then we're speeding up just in a negative direction because our acceleration is also negative. So we're going faster backwards. So that's what that is talking about. And we'll come back to that a little bit too. I have it in writing later on. When does a particle move at its greatest speed? So the greatest speed, another thing I have in just a minute, speed is the absolute value of velocity. Speed is always positive. Velocity has direction. It could be positive or negative, but speed is always positive, it's just absolute value. So when is the greatest speed? Well, it could be right here, or it could be down here. We don't have this axis labeled, but that looks like it's about the same. So I would say for C, the speed is greatest at t equals 0, and from when t is 2 to 3. That's when the speed is the greatest. One of those might be a little bit bigger than the other. It's tough to tell, but they look about the same. And then when does a particle stand still for more than an instant? It stands still when the velocity is 0. When is the velocity 0? When does it stand still? It stands still here, but only for an instant. It stands still here, but only for an instant. And then it stands still here from 7 to 9. Because that's when the velocity equals 0. This point would be the part where it's trying to trick you, because that's another flat point where the acceleration is not changing, but the velocity is staying the same. Like it's moving in the negative direction at the same speed for a little while. So it's like you put your cruise control on. So that's an example of things we can see from these velocity graphs. Other things we can do, we have some particle motion. So a particle moves along a line, so its position is given by the function s of t equals t minus 2 squared times t minus 4, where s is measured in meters and t is measured in seconds. So this is a fairly typical type of equation, a particle moving along the line, because it gives us the application, it gives us questions, but a particle, it's just a single dimensional thing. We don't have any kind of other forces acting on it, so it's like that nice clean physics problem where we don't have to worry about wind resistance and stuff like that. And it's at one specific point. It's not from here to here, because like if it was a ball, well, technically like a baseball is like 3 inches wide or so, so it's taking up more than one point in space. A particle does not. So we can find the instantaneous velocity at any time t. Part A is asking us to find the derivative. S prime of t will equal that velocity. So we need to find the derivative. We have a couple different options for finding the derivative of this one. We can multiply it all out. Start out by squaring to get t squared minus 4t plus 4, and then multiply that t minus 4 into that to get the cubic function. That's one way we could do it, because then we just have a polynomial. The other way we could do it is we can use the product rule. I'm going to do it that way, just so that we can have another example of product rule. So I'm going to set u equal to t minus 2 squared, and v is t minus 4. So the derivative of u is going to be 2 times t minus 2, and the derivative of v is just 1. So our derivative, s prime of t, which could also be written as v of t, is going to be, I'm going to go du times v, so we have 2 times t minus 2 times t minus 4 plus, then multiply these ones, u times dv, which is t minus 2 squared. Now technically this is the derivative. Calculus, AP Calculus test, we could leave it right like this. We're not going to. We're going to simplify this. One, because it's going to simplify down kind of nicely. Two, because this looks ugly. And three, because part B, we have to find the acceleration, which means we're going to need to find the derivative of this. And I don't want to find the derivative of this. That's going to be disgusting. That's going to be a whole nother product rule and stuff like that. So I'm going to say v of t. We're going to have 2 times, multiply these guys together, we get t squared minus 6t plus 8, and then plus, square that, t squared minus 4t plus 4, right, because that's not t squared minus 2 squared. Don't be that guy. We can distribute the 2 through and combine our like terms. So we have 2t squared plus t squared is going to be 3t squared. We'll have negative 12t minus 4t is negative 16t. And then 2 times 8 is 16, plus 4 is plus 20. So our velocity at any given time is going to be 3t squared minus 16t plus 20. If we were looking for our units, see, we had meters and seconds, so we have meters per second. B, find the acceleration. The acceleration is just going to be the derivative of the velocity. So 3t squared, multiply the 2, get 6t minus 16. The 20 is a constant, so it goes away. We have another, we're divided by seconds again, basically. So we're going to have meters per second squared now. So that's the acceleration at any given time t. So part C, when is the particle at rest? The particle is at rest when v of t equals 0. And it's only going to be at rest for a moment because it's changing directions from going to positive to negative or negative to positive. But we want to find when the velocity equals 0. These will give us the maximums or minimums of the position function. So when is that 0? We know that v of t was 3t squared minus 16t plus 20. Set that equal to 0. which means we're going to need to factor this. So we'll have a 3t and a t. 20 could be 4 and 5. If we multiply one of them by 3 and add them together, that could be the 4 times 3 will be 12, plus 5 is not 16. 5 times 3 is 15, plus 4 is not 16. 20 could also be 2 times 10. Obviously, 3 times 10 is going to be too big, but 2 times 3 is 6, plus 10 is 16. So it'll factor to this, which means t could equal 10/3 or 2. So the particle is at rest at 10/3 of a second and 2 seconds. So it's not actually an or, it's an and. So at rest when t equals 10/3 of a second and t equals 2 seconds. So it's at rest both times. And then describe the motion of the particle. At what value t does the particle change directions? Well, it changes directions at 10/3 and 2, but describe the motion. So we know it's changing directions then, but is it going from forward to backwards or backwards to forwards? We don't know right off the top of our head. So we're going to bring in our factored form, because we're still using that. And I'm going to make a number line. A lot of times this is also called a sign chart. So we have 10/3, which is going to be 3 point something, so that'll go over here. And 2 seconds is over here. We know at those 2 points, our velocity is going to be 0. That's a v of t. We know it's going to be 0 there. The question is what's it going to be in between there? So we just need to choose values, because it's not going to change any time other than those points. Like everything under 2 is either going to be positive or negative. So we need to pick a value. I'm going to pick 0. Plug it in. Plug it into the factored form, because we actually don't care what the value is, just what the sign of it is. So if we plug in 0 here, we'd get 3t, that's 0, minus 10 is negative. 0 minus 2 is negative. A negative times a negative is going to be a positive. So everything before 2 is going to have a positive velocity. We can pick a number in between 2 and 10/3, like say 3. 3 times 3 is 9, minus 10 is negative. 3 minus 2 is positive. A negative times a positive is a negative. So it'll have a negative velocity between those two numbers. And then if we pick something big, like say 10, 30 minus 10, that's positive. 10 minus 2 is positive, so we get a positive. So it will be moving to the right when it's positive, and to the left when it's negative. So if we were to describe if we were just to describe it, it would be moving to the right from 0 to 2, because it would have started at 0, and then move from the left from 2 to 10/3, and then back to the right from 10/3 to just whatever from 10/3 on. We could make a number line too sometimes. So we can have, I'll go purple. So we move to the right for a little while, and then at t equals 2, we're going to turn around and move to the left, and then we move to the right. Now, this particle is not actually going up. The up is just showing the time change, as opposed to having the line all on itself. And so we're moving this way. Putting arrows on the line is usually good too, and then it changes at t equals 2 and t equals 10/3. So sometimes you'll see little, like, I don't want to call them graphs, but kind of a graph, kind of like that, showing what it is that it was doing. If this wasn't a particle in motion, if it was a function, it would look like we'd be going up until 2 and then down until 10/3, then up again. So that's what that cubic function looks like if we wanted to graph it. So knowing what the derivative is doing can tell us a lot about the function itself. Another type of problem here is going to be a projectile motion problem. And this one's on the moon. That way the numbers get changed up a little bit, because when stuff's always on Earth, the numbers are always the same. And we'll see what those numbers are in a minute. So it says rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second, which is about 86 kilometers an hour, reaches a height of s equals 24t minus 0.8 t squared meters in t seconds. So what's important here is we have the position function, and it's in meters per second. So A, find the rock's velocity and acceleration as functions of time. So we just need to find the derivative. So A, the velocity is going to be the derivative. It's going to be s prime, which is, so 24t becomes 24 minus 0.8 t squared times 2 is 1.6 t. And the acceleration, which is v prime of t, which is s double prime. The 24 goes away, so the negative 1.6 t becomes just negative 1.6. And this was meters per second. This is meters per second squared. And then it says that the acceleration is the acceleration of gravity on the moon, which is negative 1.6 meters per second squared, as opposed to on Earth, we have 9.8 meters per second squared. How long did it take the rock to reach its highest point? Well, how could we find its highest point? Its highest point is when it changes directions, when the velocity equals 0. So 24 minus 1.6 t, we just need to solve this. So we can add the 1.6 t over. 1.6 t equals 24. Divide by 1.6. So it reaches its highest point at 15 seconds. How high did the rock go? Part C. C, height. How do we find height? We don't find it with velocity or acceleration. We find height with that original distance. This is the height of it. Well, how is this involving calculus? The last step involved calculus. We had to find the time. We used calculus to find the time. Now we just need to plug it in. So we need s of 15. So it'll be 24 times 15 minus 0.8 times 15 squared. So that maximum height is 180 meters. Now, could we have done that a different way? Yeah, with a quadratic. That's a parabola. This is just the vertex. We could find that the vertex of a parabola, negative b over 2a, and then plug that in, and we could get that. That's great if it's quadratic, but if it's not a quadratic, you have to use calculus. So honestly, calculus is easier. So, and if you just took like y equals ax squared plus bx plus c, and you find the derivative and then solve for it equaling 0, you get negative b over 2a. That's partly where that comes from. So C, how high did the rock go? D, when did the rock reach half its maximum height? So D, well, what is half its maximum height? Its maximum height is 180 meters, so we need, when is it at 90 meters? Well, the height, that still goes in the s. So we're going to go 90 equals, and then it's the s equation, 24t minus 0.8t squared. Set it equal to 0. We're just solving a quadratic now. I'm going to move everything over this way. 0.8t squared minus 24t plus 90 equals 0. And we can solve this. Is this going to factor? It may or may not. I don't know. We're going to use quadratic formula because that seems like it might be a little bit easier in this case. So it's when t equals negative b, so that's 24 plus or minus the square root of b squared minus 4 times a times c all over 2a. So we have 24 plus or minus the square root of 24 squared is 576 minus 4 times 0.8 times 90 is 288 all over 1.6. So that'll be 24 plus or minus the square root of 576 minus 288 is actually 288 over 1.6. T equals 24 plus or minus the square root of 288 is 16.97. This is why we didn't try factoring it. We'll round it to 2 decimal places. 16.97, it's 0.56, so that's a good rounding. Over 1.6. So then we can add, divide by 1.6. So we have 24 plus 16.97 divided by 1.6 is going to be at 25.6 seconds. And t equals, this is 24 minus 16.97 divided by 1.6, 4.39, so 4.4 seconds. Why did it hit half of its maximum height twice? It hit it once on the way up and the second time on the way back down. And then how long was the rock aloft? So for how long was it aloft, we would we want to know when is the height 0. So 0 equals 24t minus 0.8t squared. For this, factor out the t. So 0 equals t, 24 minus 0.8t. And so t could equal 0. Well, that was at time 0. That's where it started when it was thrown vertically upward. Or 0 would equal 24 minus 0.8t. So we can calculate that. That'll be 24 divided by 0.8, which is hopefully not very surprising to you. 30 seconds. Being that it's a parabola, it should be even about the vertex. So 15 seconds going up, another 15 seconds going down. But if it wasn't, it's from 0 to 30, so it was aloft for 30 seconds. So that is other stuff that we can do with this. And the questions are all basically the same. It has you find these things. It might word it a little bit differently, but when is it at rest? When is the highest time? Like, you're going to find the derivative. You're going to figure out when is the derivative 0, and then you might be plugging that back into the original equation. So some other pieces. So speed, already mentioned. Speed is the absolute value of velocity, so speed is always positive. The speedometer in your car actually measures the speed, at least it used to. Um, if you drive backwards fast enough to register, it will register a positive speed. Or so I've been told. I've never tried that myself. That would be dangerous and probably wrong. And as a teenager, I was never that stupid. So you can just take my word for it. If something is speeding up, that means that its velocity and acceleration are the same sign. Slowing down means they're different signs. So speeding up means they're either both positive or both negative. And we saw that on that first question. Some free fall equations. The one on the moon, it gave us the equation because we don't know that stuff. But on Earth, it's constant enough equations that they don't always give it to you. So having it, like write down the equation, is probably a good thing. That way you can plug stuff in. So on Earth, we have gravity is 32 feet per second squared, which means that the height is going to be 1/2 times 32 times t squared, or 16t squared. And that is measured in feet. And you might be thinking like, wait, no, gravity's not 32, it's 9.8. Well, yes, that's because in the rest of the world, things still fall. Gravity still exists, but they use meters. And so it's 9.8 meters per second squared, which gives us 4.9 t squared as our height, and that's in meters. Now these are free fall equations. This is if you take something, you drop it. This has no initial velocity. Like the one on the moon, we launched the rock upwards, and so it made that arc. This would be if you just drop it. So the top of the arc, the top height, would be at t equals 0, and then it's just going to fall. Yes, you can start it at different things. You can launch it upwards. You can do all sorts of stuff that will change the equation. And at this point, they would give you that equation. And you've probably seen those equations in physics. But right now, for free fall, this is what we need to know for free fall. And then some economic applications. So economics, they use this stuff. They just don't use rates of change and velocity and stuff like that. The vocabulary is different. And so this is just going to be some vocabulary. They have a few different equations. They'll have a cost equation, usually C of x, where x is the number of units being made. So it's the cost of making 7 units, the cost of making 100 units. That's what this is. And the cost of making like each unit usually goes down the more you make, because you have the equipment, you have the it's more efficient to make a bunch of them. So like making 100 units will cost less than making 150. But the difference between like 100 and the 101st and the 150th and the 151st, that'll be a smaller difference there at those higher numbers. So anyway, so we have cost is C of x, revenue is R of x, that's how much money you get in. And then the profit is P of x. And profit is the revenue, how much money you get in, minus how much money it costs you to do that. So those are a couple equations, that's how they're related. So for the derivatives, where those apply, the rate of change is called the marginal whatever. So the marginal cost is C prime of x. That's how is the cost changing for like a 1 increment unit at any given unit. It's just the derivative. So the marginal cost is the derivative. The marginal revenue is the derivative of the revenue. The marginal profit is the derivative of the profit. So that's all that those are. When it says find the marginal cost, that just means find the derivative of the cost function. Find the marginal cost for 12 units. You find the derivative of the cost function, you plug in 12. So I know it looks a little bit scary when you see it because the terminology is different, but it just means the derivative of whatever it is it's telling you. So that was section 4. lots of application. I know this went on a little bit long. I have 10 seconds to get you out of here, so I'll see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.